So my talk will be about a new injection method into applications and the attack surface. Essentially, it's a paper we wrote. And first, I want to, I guess Haya already told you about the DNS, so maybe I can skip that. So essentially, the point of this slide is to show you what the DNS does. And I guess that was clear. The point I want to emphasize is that I guess Haya mostly talked about the use case of DNS, where you use the DNS to find the address of a server, which is the typical use case. But actually, the DNS has many other use cases. And essentially, in this paper, we will look more into these cases. And essentially, I want to tell you about two of them, which is in first case is, for example, you can also use the DNS to find responsible servers, which essentially adds a new layer of indirection, where you first want to essentially know what is the email server for google.com, for example. Then you get the name of the server, and then you get the address of the server. And an even more complicated case is an authorization use case, where you can actually store in sender processing framework. You can essentially store information about who is allowed to send email from a certain domain, and this is stored in DNS TXT records. Actually, the point of this, or why I'm mentioning this, is that it actually makes the format of the DNS lookups or the DNS records much more complicated, and essentially leads to a problem in applications, which we're essentially looking into this in this topic. Let's look at the agenda, and essentially I'll quickly talk about the motivation for our paper, and then we will look into different components involved in a DNS lookup, and then essentially we go through them and look at what can go wrong in those components when they handle DNS records. Then I'll provide some conclusions and an outlook, and essentially I will tell you what we are doing to prevent those vulnerabilities and what we are doing and with the developers of the software. So for the motivation, essentially we stick with the general internet principle, which is also written down in an RFC, is to be strict when sending and tolerant when receiving. And this essentially means that if you design a software which sticks to the DNS or any standard in the internet, essentially, is that you really should stick to the standard on how the formats, how data should be formatted when you're sending data, but when you're receiving and processing it. And the idea is to be as tolerant as possible to when processing this data, which essentially ensures the best practical or the best possible interoperability, because even if someone is maybe not doing it right, it doesn't matter. That's essentially the idea of this. And the point here is that the DNS generally follows this general internet end-to-end principle, which in sense of the DNS means that all validation in terms of is the data correctly formatted must happen at the endpoints, and this is typically the application which triggers a DNS lookup. And the question for our work essentially was, or still is, but we now answered it, so we are going further, is if we can abuse this feature for classic injection attacks, which injection attacks you probably know all. And for example, typical SQL injections like displayed in the XKCD comic, but also other injection attacks like even buffer overflows are kind of like a type of injection attack. And there are, depending on the application, there are really a lot of types of things you can inject data into and probably cause trouble. And we will look into those. Right, so let's look at the components which are involved in such a DNS lookup. And essentially there are 4 of them, and we will start at the application, which is like the application which wants to trigger a query because it wants to know some information from the DNS. And essentially the application triggers a query, and this query is forwarded to the name server over some chain of stub resolver, etc. We don't really care about that path, but we care about the path which is like the path back, because in the second step, or the second component we are considering, is the name server, and the name server stores the data which the application wants to have, essentially, right? And in our case, the name server is essentially the attacker, as it provides the data for the domain which the application is querying. And the point here is that this data, since we assume that the name server is controlled by the attacker obviously can send any data and can put any format violations he wants to do. And any of these three components, the resolver, the stub resolver, or the application, needs to handle that. And we will now look at essentially these three components and look at which of those are hopefully handling those misformatting stuff. Looking forward, none of those are doing it, but that's the point. So essentially, there's the resolver, and as I said, essentially the resolver treats the data transparently as much as it can. This is, for example, to like allow new record types. So even if the resolver doesn't understand a new DNS standard, since it's treating it transparently, it still works essentially. That's a good principle. It just means that the resolver can't be essentially interpreted as a line of defense when looking for such injection vulnerabilities. And then there are the stub resolvers or DNS libraries, which are essentially the components which translates the DNS wire format into the textual form you all know, like with the dots, www.google.com. And typically they provide an API to the application in some form. There are different kinds of APIs for different use cases, but that's the idea. And then there are the applications which wants the data and then handles it in some way. That really depends on the use case. Obviously, if you're doing an address lookup, you just take the address and connect it. And that's actually a case where that there can't happen much in the application because the application is really dumb in a sense. But if you have more complicated lookup types like the SPF example I told you about, for example, then you have to essentially parse the record, and then it gets complicated. Yeah. Right. So let's first look at DNS resolvers. And as I said, they should handle the data transparently. And even then, even here, there's already an issue, which kind of gets to the problem, because in DNS, there's essentially two formats for domain names. And the first format is like text format, you all know, where you have a domain like google.com, for example, which is just a string, and there are labels, and then there are dots, and the labels are just the text between the dots, essentially. And then there's the wire format, which is actually the format the DNS standard essentially thinks about domain names, where you actually have a list of labels, and in the wire format, you prepend the length of each label to the label, and then just stick to each other, and the length of the last label is set to 0, so you know that the list ends there, essentially. And so the problem here is essentially what we discovered, or what at first that's like a theoretical evaluation of the standard, and when we look at if there's some vulnerabilities, but theoretically there's a problem here because those two formats essentially have different capabilities of storing values. Because the wire format essentially, since you prepend the length, you can put anything in the label, and the domain name is still valid. And actually, if you read the DNS standard, you will see that this is considered a valid domain name. So if you consider only the DNS, then a label can actually contain any value, especially this is a 0 byte and the period. And both of these special byte values essentially can create a problem if you transform this wire format into the text format, because the 0 byte would typically pre-interpret it as a string terminator, and then you would actually just stop reading data. And the period sign will be interpreted as label separated. But it is not one, and that can also be an issue. And so now I'll tell you about what you can, or why this is a problem, why I'm talking about this weird technical stuff. Essentially, you can create first an theoretical attack, but we will later see that it's actually practical, where you trigger a query to an attacker controlled domain, which is conveniently called attacker.com. And essentially, the attacker sets this domain up because he owns it, right? So he can do anything. He points this domain to a subdomain of his domain, which is victim.com, and then a 0 byte, and then he puts .attacker.com. And what this is it essentially makes this domain a subdomain of attacker.com, because this subdomain of .attacker.com. But since he puts a 0 byte after victim.com, if their resolver isn't handling the records correctly, he will essentially interpret the domain as just being victim.com. And if you then read the line, because since it's a subdomain of attacker.com, he can provide the IP address for it. If the misinterpretation happens, we will test. you will read that victim.com has the IP address 6666, which is the IP address of the attacker. And so what this means is that you can actually really simply hijack any domain you want, which is, and such an attack is much simpler than a typical cache poisoning attack where you have to send lots of packets or have to attack the name server, etc. And in this case, you would only have to trigger essentially one domain, which is the attacker's domain. And now you will say, okay, but the DNS resolver implementators or the developers of those applications aren't stupid, right? They know about this. And they kind of are. So we tested well-known implementations which weren't vulnerable, and we also tested public resolvers where we also found only one vulnerable. But then we tested the general internet, essentially just open resolvers. And there we found that actually 8% of the devices we tested were vulnerable. And this is really not expected if you only consider the well-known implementations, etc., which shows that there is essentially that there are lots of devices which aren't sticking to the standard and which you wouldn't consider if you're just looking at the big implementations everyone knows about. And those implementations aren't open source also, so it's really complicated to find out about them. And what we are currently doing in a follow-up research to the paper is we are looking into the DNS implementations in embedded routers, essentially, as our data from the Open Resolver study suggests that the problem essentially exists in those devices. That was in the DNS resolvers. So we essentially can conclude that the DNS resolvers handle data transparently, but in some cases they even have vulnerabilities. And if we now look further down into the components chain, as presented in the start, we will look at stub resolvers and the libraries. So these are the components which essentially translates the packets the host receives into a format which the application can knows about. And there's another problem here, which essentially is that essentially there's a difference between what the DNS standard considers valid data, which is the domain and everything I told you about. Essentially anything you can put inside there is valid, and what a typical application would consider valid data as coming from the DNS. Because for the DNS, I said there's a term of the domain name, which means essentially any data you can put into the packet is valid. But then there's also a standard about host names, which is an ancient RFC actually, which even predates the DNS. When you haven't the DNS, you had these hosts TXT files where you just had all IP addresses and all host names inside a file essentially. And this standard says that a host name can only contain alphanumeric characters. And this is still the standard, essentially standardizing stub resolver behavior, so those library functions till today, which if you read that like strictly, you would find that the stub resolvers should validate this data and therefore essentially protect the application from a typical injection attack, kind of, because it would validate the data. However, we tested this, and typical or the most common stub resolver implementations, and found out that only one stub resolver implementation, which is glibc, validated this data, and every other implementation was vulnerable in the sense that it exposes the application to such an attack. And they also misinterpreted the payloads I sent you previously, but that's not necessarily the point here. So the takeaway here is essentially that since the stub resolver and the resolver are treating the DNS data transparently and they're just forwarding it to the application, this essentially creates a scenario where the DNS is just another input to the application, which you would consider the same to a typical input which your application would receive from, for example, like a text input field of a website or something. And now let's look at applications. And the problem here is that essentially you would think, okay, so since the resolvers and the stub resolvers aren't validating the data, the applications have to validate it. And we tested this by essentially, we looked at source code reviews of typical applications listed inside the table here. And we found that none of the applications had some validation code which would like sanitize the data when it comes from the DNS before it does something else with it. And we also found that 8 of those applications had actually exploitable vulnerabilities due to this. And so you would think, okay, what makes an application exploitable, in a sense that if all of them are not doing what I told you, what makes an application exploitable? And essentially it comes down to that the application has to be able to trigger a DNS query to his own domain, because otherwise, so that's our attacker model, right? And the other thing is that the query result of this unvalidated thing has to be used some way in another context, because otherwise the attacker can only like do weird stuff with his own lookup process, but he can't do something to another user, essentially. And if the attacker can only attack himself, that's not really an exploit. And essentially, so that makes some applications exploitable, but others not. But all of them are vulnerable in a sense that they don't do validation. And the problem essentially about those applications, maybe to go a bit deeper, is that to an application developer, the problem here is that the DNS doesn't really look like an input vector where you would typically consider malicious input to come from. Because essentially the application calls an operating system function and he gets results back from it. And so essentially the data seems to come from the operating system. And so you wouldn't typically consider this as untrusted data you have to validate. And since there are also 2 other components, which is the stub resolver and also other resolvers, in our study with most of or when we talk to the application developers, most of the application developers weren't aware that this actually is an attack vector you can use as an attacker to inject data into the application, because they thought, okay, but there are other components in there which should validate the input, right? And we will essentially that's the problem here, is a bit that you have like, there are 3 components and each of the components could validate the data, but since there's no standard which says who should do it, essentially none of them do it, and that leads to vulnerabilities. And now I want to present 2 example vulnerabilities we found. One of them is an OpenVRT, which is an aftermarket operating system for home routers, essentially. And in this case, you can essentially take control over the router fully by injecting malicious input. In this time, it's JavaScript code inside the administrative interface of the router by essentially including it in the reverse DNS name of your own IP address as an attacker. And what it will happen is essentially then if the administrator opens the connection page, just because maybe you can like lead him to that because you say, oh, okay, there's a problem or something, the router will essentially display all connections going through it, and the router will also try to resolve all the domain names of those IP addresses, essentially, and then they will include it in the HTML file unvalidated, because obviously, or as it seems, the developers of this application isn't aware that this is essentially a way of injecting or bad input into the application. And in our example exploit here, essentially we put JavaScript code into the domain, which isn't shown here. And what this will lead to is essentially it will execute script code into the browser. And the script code then has the same credentials as the administrator, which is currently administrating the router, which will mean that the script can essentially do anything to the router. And in our example exploit, the script essentially flashes a new firmware to the router, and so it essentially, the application can gain full control over the router. You don't have to do this via this fancy script overlay. Obviously, you can do it in the background, so the administrator doesn't see it. And it will essentially lead to the router to being compromised and essentially just running a fully attacker-provided firmware, which essentially means that the attacker now has full control over the router. And then typically over the network, the router is connecting to the internet. Right. And then I want to tell you about another exploit we found, which is another application in the table before, which is edirom, or more precisely a RedSec proxy, which is a proxy server for radius connections, which is typically used in edirom. And in this instance, edirom essentially, I'll just explain it during the attack. So the attack works by the attacker triggering a DNS lookup as always. And in this case, this is by connecting to an edirom access point at some institution. And essentially how edirom works is that you have these usernames. As I told you, maybe like in the beginning, we had this discussion that DNS can also be used to find responsible servers for a domain. And as you probably know, since you're academic researchers, in edirom, you have these usernames, which are just like normal email addresses. Maybe they are even your email address. And in this case, we have a username like attacker@attacker.com. And what this username actually tells the authentication server is that you have a user attacker and you are located at an institution, which is attacker.com. In this instance, typically that would be a normal university. And this tells the server that he has to contact the authentication server for this institution and then ask it if you are really have the username attacker, essentially. And so what this will lead to is that the radius server will actually make a lookup for the organization in the attacker's username, which is attacker.com. And so it's controlled by the attacker to find the authentication server for this organization. And then this DNS records, or the proxy is essentially using this data by creating a dynamic configuration entry into its configuration. And the problem here is that essentially the payload is included in this configuration unvalidated. So essentially what the attacker can do is, since he runs the name server, he can essentially paste anything into the dynamically generated configuration by including it in the DNS records. And then you can essentially do weird stuff to the proxy. And the most interesting exploits here is probably that you can crash the proxy, which means that at the institution you are currently at, there won't be any edirom servers anymore. So essentially the Wi-Fi becomes unusable, which is actually pretty problematic to the institution probably. And you can also have unauthorized network access in a sense that you can use edirom, even though you don't actually have a valid account. And there's some other exploits as well where you can do anything essentially which you could do as an administrator who specifies the configuration. And in this case, we notified the developers and also the Deutsches Forschungsnetzwerk about the vulnerability already. However, since the configuration generation code is a bit complicated, you actually have to install the update manually, which is a bit unfortunate, but yeah. Anyway, let's just look a bit at the conclusions and the outlook. And essentially our conclusions of our paper is that in this topic, there's essentially a lack of clear responsibility which component should validate input which comes from the DNS. You say that, or there are three components: the resolvers, the libraries which parse the data and give it to the applications, and the applications themselves. And there's no standard which essentially says which component should do this. And what this leads to is essentially that none of the components do it, instead of like all of them do it, which would be the ideal case essentially. And also that there's missing knowledge by the application developers, and this prevents those developers implementing any validation in the applications typically. And what we're currently doing is we are working with the developers of those applications to fix those vulnerabilities, which actually led to many CVE entries already. And we also proposed some patch code, etc. And currently we're also pushing for more standardization in terms of that we're contacting the implementations of stub resolvers and essentially discussing with them that they should implement validation in the stub resolvers, because essentially if you do it like that, you still kind of stick to the internet end-to-end principle, and you're not validating that in kind of a standardizing form, but you also don't have to essentially change any application in the world to fix those vulnerabilities, because that's probably infeasible as always in the internet. Right, that was my talk, and thank you.